In this video, I want to do several hardware-based techniques for storing a page table. So the first idea is that maybe you could just have a ton of registers, right? So maybe on my CPU, right, I can say, oh, I have 256 registers, and these ones I'm basically going to use to store this information that shows how does this page map to which frame. So I could do that. That would be the most simplest thing I could do. This is not such a good idea. Maybe think about that for just 1 second. Ask yourself, why would it be a bad idea to have dedicated registers to keep track of where pages are supposed to be stored? Well, the issue with that is kind of simple. First of all, registers are precious. We don't want to waste them on things we don't have to, so that would be bad. Second of all, that kind of gives us a limit, right? So I can only have 256 pages active at a time. So yeah, that kind of is a hard limit there. Maybe I can avoid that as well. That gives me basically a bound on the largest process I could ever create. So that idea is, it's okay, but we can do better. So put an X next to it. Next thought. What if I instead, of storing it as a register, I store it in main memory? So I could basically have some dedicated space in my main memory that's like, this is where my table is going to be. It shows this, maps to this. I could do that. In which case, maybe I just have kind of one register, right? So I have something maybe called this, page base register, which stores the offset to main memory where that table exists. Okay, and then that table, I can make it as big as I want. That's kind of be nice, right? It's going to be a little more flexible than the previous thing. So do we want to do that or not, right? Any idea there? Think about that for 1 second. So in this case, again, it's going to be an iffy thing. Here we get hit with is basically performance, right? So the previous example, or the previous idea was to use a register. Registers, we're not using the CPU. We basically don't have anything faster than that. Here we're saying that we need to go to main memory every time. That's just going to be slow. So we are basically, slower. So this one is basically slow, right? And this one is fast. Although we are basically, have an unlimited number of addresses that we can store now. So this over here was basically fast but limited. This is slow but unlimited. So we still want to get better. So how do we get better? What we're going to introduce is basically this idea of a TLB, or translation look ahead buffer. Now we can do better. So what we want to do is introduce the idea of a TLB, or translation look aside buffer. So the idea is I basically have a buffer that's basically it's kind of at the level of catches, right, or of registers, right? It's maybe in the first catch that stores this mapping. So we're going to have something basically called associative memory. The book uses this term, so I have it in the slides. It's not too important. Ultimately, associative memory is basically, well, it's kind of like a little bit like a hash table. It's basically this memory thing where I have indices I can look up. Maybe indices can be anything. They don't have to be look like an array. And then also there's some sort of an implication behind the scenes that maybe there's some optimization happens so that the processor, when it's looking up some address right from my associative memory, it can kind of just check them all in parallel, right? So I have something like looks like constant time lookups, right? That's why I use the idea of a hash table, but a constant time lookup, right, to figure out where does this thing belong. So that's what we'll talk about, right? Is this idea of a TLB, right? Simply with associative memory. Think of it as basically being a constant time hash table. So yeah, that's going to be our technique we're going to use here. Moving to our next slide, let's kind of take a look at what a TLB does. So a TLB, right, is basically this CPU, this low-level, it's even a piece of hardware, right, map, right, that basically lets me translate from my logical addresses to my physical addresses. So how do I do that? So my TLB is basically a little piece of hardware, right? It's got some memory reserved for it on the CPU die. What it's doing, right, is it's supporting a way for me to map from page numbers to actual memory addresses, right, to physical addresses. So let's start the diagram at the right and just kind of talk through it. So this is now going to be our process for using memory, right? And so it's a lot more complicated than things we've seen before. So process for using memory. So the first step here, right, is basically start with the logical address. And our logical address is broken into two pieces. It's broken into basically a page and then an offset. So let's look at the data flow here. For the offset, I'm pretty much good to go, right? I don't have to do anything. For the page, though, I'll have to do a little bit of work. So the idea, right, is I have my table here, right? So it's similar to the tables we talked about before, right? And conceptually, we have kind of the idea already of a page table. This is now quite literally my page table. Or rather, I should say it's kind of the upfront page table, right? It's like the stuff I have available right now. Somewhere in there, and the idea of a TLB is that it's just a buffer, right? So I may have additional things out there, additional mappings between pages and memory locations, but they're not in the TLB. The TLB has some finite size, right? So maybe it's the thing that's 256 units long. It's finite size. It's just a buffer. And so what happens is that when I'm looking for an address, I'm going to go look at its page number, and I'm going to start by looking inside the TLB and see if the TLB, because it's very fast to access, has that mapping recorded. So let's say it does, right? What we say occurs is a TLB hit, right? So if my TLB contains the address that a page belongs at, well, then it's a hit, right? So my TLB was basically able to answer my question, where does this page exist in main memory? And so if it is a hit, right, then I can basically figure out where my, my variable is being stored. So I have my frame, location and my offset. I add them, right, and I get my, physical memory, right? So in that case, right, I have basically this flow here, right? I go from CPU to page to frame to TLB to math, right, to main memory, right? Maybe I should add this flow as well, right? So it's going kind of like this. That's for something that my TLB knows about, right? Some sort of situation where my mapping exists in my TLB. My TLB is a buffer, right? So it's a table, and a table is basically going to maintain just some set of the overall mappings, right? So there are, a million pages out there, but my TLB is a lot smaller. My TLB records, just a few mappings, right? And so if it happens to be, the page I'm looking for, right, happens to be one of the ones that's stored in my TLB, right, then I'm good to go. That's the case we kind of talked through. The alternative, though, right, is what happens if I have a TLB miss. So let's say I go to look up a page, right, and that page number isn't in that table. What do I do? Well, in that case, I have to go to main system memory, right, which has a second page table, and that second page table, I have to basically look up and see, where is this thing being stored. So I'll take this route here. This is basically what we call a TLB miss, right? So a TLB miss basically is saying that I went to look up a page in a TLB, and it wasn't there. Okay. In that case, I have to basically go to main memory and find out where the page is located, right? So this is going to be a lot slower, right? So this is kind of the slow route versus this is the fast route over here, is basically what we're saying. Okay, so I have that stuff set up. Now, what do I want to do? Okay, so this point basically I'm done, right? I have my two routes. So whether my TLB contains it or it doesn't contain it, I still have a way to get the address at the end of the day. A note here about kind of words. This over here is a TLB miss, right? So if I look for a page and it's not in the TLB, then I have a miss. So yeah, that's the overall idea of a TLB-based memory lookup process. Some additional details. Sometimes these addresses in here will basically be wired down, right? So some of these addresses, let's say these first over here, might basically permanently reside in a TLB. Versus the other addresses in there are basically going to be based on what program is running, right? So if one program is running, probably its pages, right, that mapping is going to be available on the CPU because it's been running a lot and doing a lot of stuff. Versus another program that maybe isn't so active, it won't have entries in the TLB, right? It'll only be known about in the main memory page table. So that TLB, right, because it's a finite size, you only want to use it to store the page mappings for the processes that are active, right? Because that'll speed them up. We don't need to speed up a process that's not actually running right now. Just the ones that are running are the ones that count. So we kind of maintain that, right? And we're actually going to talk about different rules for kind of maintaining this, the basically what pages are available. There are kind of different algorithms for doing that. All right, so the things that are wired down, right? So that's basically saying that I have some addresses that I'll never move out of my TLB. Maybe we'll take 1 second to ask yourself what type of addresses those might be. Well, those addresses are typically something like a kernel level file, right? So maybe I have, or a system level process, right? Basically something that's OS based. So if the OS has, a driver for using a keyboard, probably that's a driver that's going to be used a lot. So we're going to be running its code a lot. That means we're going to be using the TLB a lot. Probably want to basically just keep those addresses there, right? That mapping there. So when we want to, run that particular, code for accessing the keyboard, it's always going to be there. So really key stuff that happens a lot, that typically is what we'll wire down. Now the page table also, kind of in addition, right, to basically being this data structure we use to maintain these mappings, also I can kind of add some meta information. So one thing here it suggested is this idea of address space identifiers, or ASIDs. So that's basically like adding a note to our page tables, to say, this process owns this particular page, right? So if I extend this a little bit, right, you can imagine, right, I'll have somehow, it's a little number on there. It says, this is owned by program 1, program 2, program 0, whatever, right? That would be kind of another extension here. And that's just kind of nice from a security standpoint, because then we can say, well, if you're doing a TLB lookup, are you doing it for a page that belongs to you? If it's not, well, then you're not allowed to access it. So that is a little bit nice. The final note for this slide is something basically on performance, which is the idea basically of calculating how good our lookups need to be. So what we have here, right, is this idea of basically a hit ratio. So how many hits does a TLB get versus how many misses? Obviously you want to have as many hits as possible because that speeds up my process, right? It's very fast for me to go through the TLB versus if I have a miss, right, I have to go through the main system memory, look at my page mapping, well, that's going to slow me down, right? That takes a lot of time to access that other memory. So I want to basically figure out, what sort of performance I'm getting from something. So the idea here, right, is that's something called, this TLB ratio, right? And so a TLB ratio, for example, 90 means that 90% of your lookups, right, were found in the TLB. That's very nice. And so if we want to, right, based on our TLB, kind of our lookup, we can basically figure out, what is the average time for me to find out, where something is located. So in this case, right, I have this formula here. And it's kind of, blended in a little bit. But what we have here, right, is this, the average, basically it's average or expected, memory access time. And what I do there, I'd figure out, how much time on average it'll take me to access something is say, well, I'm going to multiply basically my hit ratio, right? So that's the number of times I get to use my TLB by the amount of time it takes me to access the TLB. And then the other one, right, is basically 1 minus hit rate. So those are the misses times the main memory access, right? So I have that little formula there. Basically, I'm going to be able to compute what is the average time I could expect to to look up something, right, based on how many hits I get. And this is actually going to be a little bit useful for us because what we can do is basically solve for, like if I want to have, an average waiting time to look up something like, 20 milliseconds, you can imagine I take this expression set equal to 20, and then I can solve for the hit ratio, right? So I can do a little bit of math there, a little bit of algebra there, basically to figure out, if I want to have this system performance, what does my TLB need to act like? So it gives me a little bit of information for any sort of design process.